So I will start. So hello everyone, I'm Victor Kalt, a PhD student from the LMRS at Rouen, and I'm doing a PhD studying quantum turbulence in Bose Einstein condensates, and my physics advisors are Danaya from LMRS and Marc Brachet from ENS. And today I will talk about the identification of vortex lines in simulations of Bose Einstein condensates. So this work was done in collaboration with George Sadaka, that's published this morning on FreeFEM, on the basis of a previous study that was done by Pierre-Emmanuel Emerio, Frédéric Hecht, and Yannick Danaya. So quantum fluids, and among them Bose Einstein condensates, are home to many interesting phenomena. And one key point in the understanding of these phenomena is the presence and the behavior of vortices. That's why we want to study those vortices and know information about them, such as the number of vortices, their location, the radius, and things like this. So here we have examples of Bose Einstein condensates. So here a small condensate that is rotating on itself. So here we have only one vortex, here two vortices, three vortices, and so on. And the number of vortices increases because the rotation frequency augments. So here you have a low rotation frequency, here we have a high rotation frequency, and we see that you obtain a triangular lattice of vortices, known as the Abrikosov lattice. Here we have a larger condensate of sodium atoms from MIT, and we can clearly see the triangular lattice. So what exactly is a Bose Einstein condensate? It's a new state of matter that's obtained when a dilute gas of bosons, so integer spin particles that are subject to the Bose Einstein statistic, are cooled to temperatures near 0 Kelvin. When this is done, all particles will be in the same quantum state, which is the lowest energy state. So another type of quantum fluid with a different physics but similar phenomena is superfluid helium. So superfluids are fluid with vanishing viscosity when they are cooled at low temperatures of around 1 Kelvin. So the physics is different, but those types of quantum fluids can be modeled in the same way. The model is a complex wave function psi, which we can write as the square root of rho times exponential is, and we can make a link between psi and the classical quantities we know in classical fluids, that are the density, which is linked to rho, and the velocity, which is linked to the gradient of the phase. Since we use only one wave function to describe a system made of many atoms, we need to modify the Schrödinger's equation to take that approximation into account, and this gives us the Gross-Pitayevsky equation written here. So we have a time evolution term, the Laplacian, a potential that is present only for Bose Einstein condensates, and it corresponds to the trapping of the atoms, because they need to be trapped electromagnetically to stay together. So usually it's an harmonic potential, and it will govern the shape of the condensate. And then we have the nonlinear term that comes from the interaction between the atoms, and a rotation term with an angular momentum operator and the angular velocity, since we are studying rotating systems. So if we take a system described by this complex wave function, we can compute the circulation of the velocity around a closed path. This is gamma. And if we do the calculation, we find 2 pi q, where q, the winding number, is an integer. If q is non-zero, then this means that there is a phase defect inside the area enclosed by C, since the velocity is linked to the phase of the condensate. And as the wave function is single-valued, this means that in this point, the density must be 0. We then have the definition and the two properties of a quantum vortex. It's that it's a point in 2D or a line in 3D with 0 density. And if we compute the circulation on a closed loop around them, we will find plus or minus 2 pi. So I will ignore vortices with Q different from plus or minus 1 because they are unstable thermodynamically. So I will not talk about those here. So here you have a vortex line in blue that will correspond to the minimum of the density, so 0. In red, we have a region where the density is low compared to the background. So we can call this the vortex tube, and it has a given radius. And here, in blue, we have a circle where if we compute the circulation, we will find plus or minus 2 pi. So those are the characteristics of a vortex. So the simulation I'm presenting here are performed in Fortran using the code GPS from Gross-Peterevsky simulator, using a backward Euler method if you want to find the ground state of a condensate, so in the time-independent case, or a time-splitting method from the time-dependent case for the time evolution. We can also solve this GPE in FreeFEM using the toolbox GPFEM, which implements a Sobolev gradient descent or a minimization of the condensate energy with IP-opt. So this is only for the stationary case. Once the simulations are done, we want to identify vortex information and in 3D vortex line information, which is the main goal of the presentation. And this is done using FreeFEM and finite elements. So I will start with a 2D case. So here we have in figure A a plot of the density, so the modulus of a wave function. And we see the background density, which is an ellipsoid, as we use an harmonic potential. And we see holes that correspond to the vortex, so minimums of density. So the first step to know information about the vortices is to separate them from the background, which is done by removing the Thomas Fermi density, which corresponds to a solution that is analytic to the Gross-Peterevsky equation, where we remove the Laplacian term. So this Thomas Fermi density is presented here in figure B. Once this is done, we obtain what is plotted in figure C with spice that corresponds to the different vortices. Now, to isolate the vortices, we need to compute isolines, which is done using the isoline function of FreeFEM, and we get what is presented here in figure B. So we have isolines that corresponds to the density minimums. Once we have the isoline, we can build mesh inside the isoline and verify the second property of the vortices, that is the circulation of velocity. So we compute the circulation of a velocity on the isoline, and if we find plus or minus 2 pi, then we have identified a vortex. To know information about the vortex, we can now fit a Gaussian einsatz, that is done with IP-opt, and this will give us the vortex radius and the coordinates of the vortex center. So in figure D, we have a mesh where all vertices are vortex centers. And we see that the small isoline in the left of figure C has been removed because it's a density minimum, but the circulation is 0. So on figure D, we obtain the number of vortices, their center, and we see that we obtain the triangular lattice, so the Ambrikos of lattice. The goal in 3D is quite the same. So here we have the isosurfaces of low density in superfluid helium. So we see here we have a simulation box and no potential. So the vortices are present in the whole box. And here the lines that have been identified from this simulation. So the identification process is an adaptation of a method presented by Liu et al. In 2019, an adaptation because we try to reduce the computational cost of a method, and we adapt it to use non-structured mesh and finite elements. So the first step is to reduce the mesh size because many tetrahedrons in the mesh are not interesting because they are not associated to vortices. Those are the tetrahedrons where the density is high, so we start by truncating them using a density threshold. And those are the tetrahedrons that are outside the Thomas Fermi radius, so outside the Thomas Fermi density. So again, they can be removed because there can be no vortices there. Once this is done, we need to verify the circulation property, and we talk about this in the next slide. And we can remove tetrahedrons where we find 0 circulation. The last step is to separate the regions. So here we see that you have multiple vortex lines that corresponds to non-connected regions of the mesh. And we can separate the problem by studying those regions separately. So an example is presented in figure B here, where we have one region that will contain two lines. So to approximate the circulation, well, we need to go back to the definition of the circulation and to the phase of the wave function, which can be written as the imaginary part of the logarithm of psi. Since the velocity is the gradient of the phase, we can approximate the circulation on 3 points with this formula, which represents the integral of the gradient of this quantity. And then we can apply this on all the triangles of the mesh. So this is a rough approximation, since it's only on 3 points. But if we do this on all triangles of the mesh, we can create a P1 finite element function that will be 1 if we find a non-zero circulation, 0 if we find a zero circulation on all points of the triangle. So if we look at all the triangles with non-zero circulation, which we will obtain this graph here, where we can see some defects here created by the approximation here on only 3 points. But it's still quite accurate, and it's enough to obtain a good reconstruction of the vortex line. So sometimes some defects can stay, and it is necessary to remove them, but most of those won't cause any problem. So now the second interesting part is the separation of the regions. To do that, we solve the Laplacian equation, so minus Laplacian of u equals u0, with u0 being 1 in one vertex and 0 elsewhere. So when we do that, we obtain a solution that is non-zero in the region, so the connected part of the mesh, where we put the one vertex to 1, and that is 0 in other regions. And we use Neumann boundary conditions. So when this is done, we can compute the minimum and maximum values of u and truncate the region from the mesh using those values. So this is done here, and we will repeat the process until we have treated all the mesh tetrahedrons. So while we are still tetrahedrons in our initial mesh TH. So this is an idea from Georges Sadaka. So the second step of the identification process is to isolate the lines. So this is done here. So we have the initial data here. We have the separated region here, and the triangles with non-zero circulation here. And now we want to reduce the number of points here. So we consider this as a graph, and we compute midpoints, which are represented by squares here. And those midpoints are connected based on the connectivity information from this graph. Here we have two non-connected subgraphs, which will mean two non-connected vortex lines. So once we have those midpoints, we can link them using the connectivity from this graph. But it's not always that easy to construct a line, because we can have different cases. The first is a single line in a single region, where there is no problem here. The second is if there is multiple non-connected lines in a single region. Even if computing the circulation is not enough to separate the lines, they can be separated here based on the graphs. Because when we are truncating, we can truncate tetrahedrons. Tetrahedrons can be linked if the circulation is one in only one face of the tetrahedrons. But using this graph here is still enough to separate the lines. The second kind of vortex lines is vortex rings, which are closed loops. So it's quite important to keep this property of having closed loops. So we must ensure that the loops stay closed, even when doing the midpoints averaging. the third kind of vortex lines, which is the most difficult one to deal with, is the case of vortex reconnection. This happens when two vortex lines intersect. So here we have some initial data, but when it's, those circles are so perfect, for a simulation of superfluid helium. And if we look inside, we can find something like this, which are two vortex lines that are intersecting. So when two vortex lines are intersecting, it's quite difficult to say which branch goes with which branch. So what is done is that we consider that if a point has a connectivity here higher than 2, then we separate all branches into separate vortex lines. This is done because when doing a time evolution, vortex lines can exchange branches after a vortex reconnection. So with this here, it will correspond to the creation or destruction of vortex lines, but not on the exchange of branches. Finally, we save the lines as mesh L to ensure that we can deal with the data after and compute interesting quantities. So to see some results, we have one example here. So the isosurfaces of low density here on the left, and on the right, we have the extracted vortex lines, and we see in the center of a vortex ring. So we kept the property of having a closed loop. For Bose Einstein condensate, the process is the same, but we also remove the outside of the condensate, which explains why we have this strange shape. Here we remove the center, that is high density, and the exterior, which is zero density, but outside the Thoma Fermi radius, which gives us this shape. So this is a simulation done with GPFEM, so using FreeFEM. If we compute the circulation, we will remove the skin of the condensate. So we have only the vortex that is present in the center of the condensate, and then we can compute the circulation and then average the points here. If we look at a more complex simulation with many vortices here, we see that the method works well because we obtain all the vortex lines that are present in the simulation. So to do this, well, this is a sequential code, and in the future work, the first thing we plan to do is to parallelize the initial data loading and the truncation of regions of low density, of high density, because since we're using a sequential code, we're limited in the size of a simulation we can load with this code. So this is what we plan to do to get rid of this limitation. Once this is done, we want to simulate condensate with many vortices, which is a state known as quantum turbulence, and then study properties of this quantum turbulence using the mesh L that you have saved. So those properties are the oscillations of the vortex line, so the Kelvin waves, and the oscillations of the vortex lattice, known as Katzenko waves. All right, thank you for your attention.
So thank you, Victor. There are some questions on this very interesting talk. Me, I have a small question. You present an algorithm in slide 12, and I think it's very expensive algorithm because you have loop on number of triangle. So which are the number of iteration in this loop? You get
here, the number of iteration, which correspond to the number of regions inside the mesh. So it's a loop until there is no triangles left in the mesh that are not in one extracted region.
So you want to compute almost subdomain?
Yes, it is this.
So I think there are algorithms to do that more rapidly. Your subdomain are defined as the zero value of some some ISO value is defined by the ISO value 0 somewhere. Or completely out.
No, we define subdomains by the connection on the mesh. This is here the total mesh in figure A, and some parts of it are not connected. We see that this part is connected to
the number of subdomains are colored here. Okay, so I can give you more fast algorithm to do that.
Okay, thank you.
I'm sure that it's basic problem of graph theory, and I can give you some algorithm to do that.
Thank you.
Okay, no more question. So I will do an applaudissement, and thanks for all this very interesting talk.